1989, and we proceed, Dr. Peierls, and then you start talking and say that essentially, if you would begin by saying, I was born in so and so at date, and start, and then I will, and we'll just carry on, and then I will ask not many questions, but I'll ask questions from time to time, and if you will just proceed informally to talk about your life and your career and the experiments and so forth in a more or less chronological order.
Yeah. How long do you expect the whole interview to be?
It varies from, depends on how things go, but from 1 hour to 2 hours.
I see.
Sometimes it lasts longer, like some people like Linus Pauling are very talkative, and it took 2.5 hours for him. And some are very reticent, and it's only about an hour, but we'll just let it relax. It's from 1 to 2 hours.
All right.
And we will get you out of here by about 11:15 or 11:30, so you'll be at the academy, so you can relax at before 12 o'clock. So I think that we're about ready to start, and it is recording now.
It is not really.
You haven't pressed the. Just a minute here. We've got. You might want to sort of on the camera remote's on. Just make sure that it's rotating.
It is.
All right. Very good. Well, today is April 25th, 1989, and excuse me, Jane, I'm going to start over again because we want my microphone also. All right, I'll start over again, Dr. Peierls. Today is April 25th, 1989, and we have the pleasure of interviewing Dr. Peierls, who will speak to us of his many accomplishments in his career in many fields of science, particularly in the fields of nuclear science. So with this, Dr. Peierls, would you please proceed?
Yes. Well, I was born in June 1907 in Berlin, or rather in a suburb of Berlin, where my father was a director of a large factory belonging to the AEG, and I quite early on was interested in technical and scientific matters. I liked reading about such things, and my wish at that time was to become an engineer, which was natural. I grew up in a technical and technological environment, and with airplanes just coming on, the telephone being relatively new, automobiles developing and so on. So naturally a boy wanted to get into that kind of life.
Yeah, that was the golden age of the start of technological development.
That's right. And however, my parents and other people I respected told me that I was not suitable to be an engineer for reasons which I think wouldn't accept today, but they said an engineer has to have good eyesight, and I was wearing glasses from the age of 6. And they also said that an engineer must be able to make things with his hands, and I was at that time a little clumsy with my fingers. So I accepted their advice, and turned to the next best thing, which seemed to be physics.
Oh, yes. Let's see, what year was that then that you actually more or less settled on physics as a career?
Well, it was finally settled when I went to the university,
Yes.
which was in 1925. But there was a gap of 6 months or so between school and university because my school had an academic year which finished at an unconventional time. And I could have joined the university straight away, but I could have got into the middle of courses, and it seemed more practical to wait 6 months. And so I spent that as a sort of unpaid apprentice in a telephone factory. Because if I'd been an engineer, of course, I would have had to spend some time in industry. That was a normal practice. And I was very anxious to do that anyway, and I never regretted having gone through that experience.
Yes, so you did, through that pathway, did get to have an understanding of the workings of a technical field, which was, of course, beginning to expand tremendously at that point.
That's right. But I also learned simple things like using a lathe and drilling machine and various things like that, which I found very useful after that. Well, I then, it wasn't, one had in German universities be fairly clear from the start whether you were going to become an experimental physicist or a theoretical one. Oh, yeah. Well, it wasn't finally settled, but in fact it got settled more or less by accident, because in the University of Berlin, where I started, because my parents thought I was too young to leave home, the practical laboratory, student laboratory for physics, was overcrowded, and therefore you were not allowed in your first year to start on the experimental work in physics, but instead you were supposed to get through as much of the mathematics and theoretical physics work as you could. And so I started on that and never got out of it. So during my first 2 semesters, I listened to the lectures by Max Planck, which were the worst lectures I've ever been to. He was reading from one of his books, and if you had a copy of the book, you could sit there and follow line by line what he was saying.
Well, that is a very interesting point, because that the experience with people with famous lectures varies considerably, all the way from being sometimes very dull and straightforward to inspirational in character.
That's
and
right.
That's very interesting that the great Max Planck was not a very good lecturer.
He was a terrible lecturer. And I mean, his books are not that attractive either.
Yeah.
We knew, of course, that he was very famous, but had no idea what he was famous for. Yeah. And in fact, the first impressions I got that there was something exciting developing in physics that was new was in lectures by Walter Botha, later known as a nuclear physicist.
Yes, a very famous man in his field.
And he was then giving a course of lectures on what was called X-ray physics. And there, such new words as the Bohr orbits and the K-shell and the quantum of action and so on appeared, which showed me that there was something that our high school physics had never shown to exist. Now, and I still remember one of my fellow students said one day, interesting things are happening. I hear that in Göttingen, Heisenberg has actually applied matrix methods to physics.
Yes, that the immediately you were in contact directly or indirectly with the great names of in a very exciting period.
That's right. Well, after 2 semesters in Berlin, I decided I was big enough to move. In those days, it was quite easy to change universities, and so I went to Munich, where then Sommerfeld was the great teacher of physics. And so then I started learning about these new things. And I remember that at some time during my 3 semesters there, Sommerfeld told me that I might give a talk in the seminar. And he said there are these papers by Dirac and by Jordan on what we now call transformation theory. And we haven't been able to understand these. Would you read them and try to explain that to us? Which was quite a challenge to a student of about 2 years standing in the university.
Yeah. You see, how you were about 19 or 20 years old?
20 years. Yes, about. I don't remember exactly when this was, but about
very
20.
young.
Yeah, but I found those papers very interesting and gave 2 talks, in fact, and I learned a lot from that. How much the audience learned, of course, is for others to say. But I had no criticism except from the professor of physics, experimental physics, Willy Wien, who didn't believe in quantum mechanics, quantum theory altogether, and therefore, of course, wouldn't accept my explanation either. And one of my fellow students there was Hans Bethe.
Oh, yeah.
Who was a year older and a year further advanced in his studies, so he seemed to me a very senior man from whom one could learn a lot. Well, we've been friends ever since. Now he is still 1 year older, but that is perhaps less important today, but I still think that I can learn a lot from him. Well, I would have continued in Munich, except that when I'd been there a year and a half, 3 semesters, Sommerfeld went off on sabbatical leave to somewhere in the United States and sent me to Heisenberg in Leipzig, who just was starting a school of theoretical physics there. So in Leipzig, there were, amongst other people there was Felix Bloch, who had written was then writing his thesis on electrons and metals. And after a while, Heisenberg suggested that I might like to apply Bloch's results to the Hall effect, the change of the transverse voltage you get if you put a conductor with an electric current into a magnetic field.
Yes, that's of course very useful in the field of modern solid-state physics.
That's right.
Too.
But it was then a paradox because while some metals behaved in the expected way, in that the transverse voltage was what you expect from the deflection of electrons by the magnetic field, some metals showed the wrong sign. And that was a problem. It was then called the anomalous Hall effect. And so I looked at this and found that you could explain this if the bands whose existence Bloch had shown if of those bands, one was nearly full, so that in fact the conduction was due to holes, to vacancies in that band. I didn't use the word holes, but I mean the concept was
the concept is the same as the modern use of holes that we use in solid-state physics.
That's right. And as these holes, which are the absence of an electron, are positively charged, you can then understand that the sign of the effect is opposite. It's like as if the carriers were positive charges. Now, that was very exciting. That allowed me to publish my first paper. And generally, it was a time when, as in this example, you just took almost any problem which had given difficulties to the old physics and looked at it in the new way, and you had removed another difficulty in understanding.
Yeah.
So that was an exciting time.
So you published a scientific paper at what age were you when you published that first paper?
I was 22.
22, that's really remarkable,
I think.
Well,
in fact, 22.
Yes.
And, well, this was fairly normal at that time.
Oh, yeah.
But then after 2 semesters, Heisenberg went on sabbatical, and on his advice I went to Pauli, to work with Pauli in Zurich. Now, I think I have every reason to be grateful to the system of sabbatical leaves or to the invitations from American universities, because this gave me a completely unique combination of teachers.
Oh, yes. That, of course, as you go through the discussions of these great men, you've mentioned 8 or 10 of them, and who are really the giants of theoretical physics at that particular time.
That's
so
right.
It must have been very exciting.
It was exciting. Of course, Pauli was not quite easy to get used to because of his famous habit of making cutting remarks to people. But one accepted that because he was such a deep thinker about theoretical physics and made things became so clear in discussions with him. So I then wrote my PhD thesis on the heat conduction in non-metals, where the conduction is due to the lattice vibrations or to phonons. That was a subject on which there was a theory by Debye. Typically, Debye in being very elegant in finding simplified ways of looking at things. But in that case, it was too simple, and his answers weren't right. Yeah. So I was able to sort this out. In fact, even Pauli had done something incorrect on the subject. He had looked at the problem of the damping of sound waves, absorption of sound waves, which is very similar to the problem of thermal conduction by lattice vibrations. And he never published this, but he had given a talk to some meeting of a physical society, and that is, as far as I know, the only paper under Pauli's name containing wrong statements.
That's a very, very interesting point.
But I think he knew that there were still problems. That's why he told me to look at this problem further. And I came out with an answer, unexpected in some ways. One result, for example, was that at low temperatures, the thermal conductivity of a crystal should grow exponentially as the temperature goes down. And that was not verified until the 1950s.
Oh, yeah.
But then it turned out to be true. And so then I it took me only one semester in Zurich to write this thesis, or to get the answers and write the thesis, which I typed myself. My parents had given me a typewriter as a present, and I've started typing, not in a very professional way, but I wrote my thesis myself that way, and I've been continuing to do that. I had to submit it to the University of Leipzig because one semester in Zurich wasn't enough to qualify for a PhD. The 2 semesters in Leipzig apparently did, and so I got my PhD from Leipzig. And but then remained in Zurich as Pauli's assistant, and I stayed, in fact, for 3 years.
Oh, yes. And, well, that must have been very, very exciting there during that period with Pauli and all of the others involved in theoretical physics.
Yes. It was a time when Pauli was working together with Heisenberg on the quantum theory of electrodynamics, quantum electrodynamics, which of course was in a very primitive stage then, but he discussed many of the aspects of this with me, so that was exciting. And meanwhile, I continued mainly to work on solid-state problems. I had written this paper on the Hall effect, and my problem was this depended on understanding the nature of the electron bands in metals, which started by Bloch. But Bloch had proved this behavior only for the case of very tightly bound electrons, where the wave functions are very, very much like atomic wave functions in the metal. Now, I knew that this was not a good approximation for real metals, and so it wasn't clear whether the conclusions of Bloch's, which I had applied to my explanation of the Hall effect, was really justified. And then I suddenly saw that if you start from the other end, where the potential in which the electrons are moving is very weak, so that you can start practically from the limit of nearly free electrons, that if you start with free electrons and add a very weak potential, you already get the breaks between bands and the behavior of the dynamics near the edge of the band in exactly the same way as in the very strongly bound electrons of Bloch. So then I was satisfied that this could be applied right through, if it was true in both extreme cases.
Yeah, those are some very, very fundamental points and research that was needed to establish the field at that time.
That's right. And in fact, I looked at that problem for simplicity in one dimension for a particle moving in a straight line. And I had understood the pointer, and I knew, of course, that the same thing would happen in 2 or 3 dimensions, but didn't bother to spell it out. But that was then picked up by Brillouin, a French theoretician, who worked out in detail what would happen in 2 and 3 dimensions and came out with what's now called as the Brillouin zones in metals or solids.
See, where was he working at the time?
He was working in Paris, I know. And, we didn't ever, well, we may have met at some conference, but I mean, he'd seen my paper. And, I saw his papers. So there were other things in that general direction, which I did. But of course, in those days, you didn't specialize, or didn't necessarily specialize in theoretical physics. Quantum mechanics was so new that you were interested in all its applications. And of course, at that time, you were expected to have read all papers that were ever published on quantum mechanics. Now you couldn't do that today.
Yes, of course, there's been such an explosion of literature on everything that whereas 50 years ago you could keep up with all of the papers, today there's 100 times as many papers coming.
Today you can't even keep up with the papers in one special field, let alone the whole. I've always been inclined to keep my finger in many pies. You know the old saying that a specialist is somebody who learns more and more about less and less until he knows everything about nothing. And I'm more of the opposite, the universalist, who learns less and less about more and more until he knows nothing about everything. That's more my...
Very good expression.
So then, after 3 years, in 1932, I was awarded the Rockefeller Traveling Fellowship, and for 1 year, and decided to split this between Rome, where Fermi was at that time, and Cambridge.
Oh, yes.
Cambridge, England. I followed in that way the precedent of my friend Hans Bethe. However, he had arranged to spend the summer in Rome and the winter in Cambridge, and I thought I would improve on that by reversing the order.
Oh yes, that's interesting point.
And so I spent 6 months in Rome under Fermi. That he was most impressive person, of course. When you ask him about a problem in physics, the chances are he would pull a notebook from his shelf and turn to a page where he had worked out the solution to that problem some time ago.
Yes. Incidentally, you say this is about 1932 that you spent with Fermi.
Yeah, the winter 32 to 33.
That was before he started work in radioactivity and so
That's
forth.
Right.
In fact, I remember his book on I believe on thermodynamics or something like that. And so he was very versatile.
Yes, and of course he was still basically a theoretician, but he had been very excited by the discovery of the neutron in 1932.
Oh, yeah.
And he already then decided that this was a very important tool for the study of nuclei, and therefore was preparing to do experiments with neutrons. But of course it took him, and I think he was already planning this when I was there. He didn't mention it as far as I remember, but of course it took some time to get the necessary apparatus and things together. So he didn't start the experiments until 34, I think, or late 33. I should perhaps mention that I was by this time married. I had been at a conference in the Soviet Union in Odessa in 1930, and that also was an exciting experience.
Oh yes, was this a conference on theoretical physics?
It was a conference on physics in general.
Physics in general.
And it was essentially a Soviet conference on physics, but they had invited something like a dozen foreigners.
Oh yes.
And I was very fortunate to get there. I think it was because Frenkel, the Leningrad theoretician, who had seen some of my papers and was interested, so he invited me. And now there was at that conference also a girl who had just finished a course in physics but come to this conference for interest. And we got to talk a lot and stayed together after the post-conference excursions, so we saw each other perhaps 10 days or so.
Oh, yes.
And the difficulty was that she couldn't speak any German and I couldn't speak any Russian, only a few words, so we communicated in English. And then we started writing letters. 6 months later, I went to Leningrad on Frankel's invitation, spent 2 months there of our Easter vacation, and within a week or so we were married.
Well, it's a very romantic story there. I'm glad that you brought that out. And so she had training in physics. Then.
But she didn't continue with physics because I think she knew that she would not be a first-rate physicist. And in fact, well, it took 6 months after we married before we managed to get her out of the Soviet Union. And that was so exciting for her to see the world that so that she dropped her physics and didn't come back to it. But she did a lot of her physics by looking after and educating many young physicists.
Oh yes, that's very, very interesting point.
And probably more than she could have done by working in physics. One traveled, of course, also in those days. It was not as easy as today because there were no foundations or other organizations dying to pay a fare to conferences, and you had to go there under your own steam.
Oh, yes.
Mostly sort of sitting up.
I believe the Rockefeller Foundation was one of the very few in existence that did anything like that at all.
Well, I don't think they would have got to a conference.
I see. Only for fellowships.
Well, maybe there would have been a possibility. But while you were on the fellowship, probably you could have got some travel money out of them. But otherwise, you would sit up maybe overnight in the corner of a third-class railway compartment. Of course, no planes in those days. There were 4 classes on the railways in those days, but the 4th class didn't exist on the long-distance trains, so it was third class you traveled. And amongst those trips, one of the places to go to, of course, was Copenhagen. And I went there for the first time in 1931, and I've been there many times since. I had a slightly embarrassing encounter with Niels Bohr on my first or second visit, I don't remember clearly. I had written a paper with Landau, the Russian, who had spent time in Zurich, and we'd written a paper claiming that the uncertainty principle needed an extension when it came to a relativistic situation. And this paper was ready when we met again in Copenhagen, and we showed it to Bohr, who didn't agree. And we had long arguments. And then, when we finally settled the final draft of the paper, we were a little doubtful whether we should acknowledge Bohr's advice and help, because we felt we couldn't do that without his permission, because very often if people cite somebody like that in a paper, it gives the impression that he supported it or agreed with it.
Yes.
And we knew he didn't agree.
There's a very subtle difference there, but which could easily be misunderstood.
Right. And therefore, I went to ask him about this, and he misunderstood. And he got very angry and said, well, he was only doing his best to help people clear their ideas, but it was only natural to acknowledge this, but if we had any doubt about it, then he refused to let us mention his name at all. So this was very embarrassing for a young man, but we eventually got it straightened out, and of course we did mention it. We didn't acknowledge his help. And in fact, that then gave rise to a paper he wrote with Rosenfeld to prove that measurements in field theory, in electromagnetic field, were restricted only by the same restrictions of the uncertainty principle that were known and applied in non-relativistic quantum mechanics. Well, this subject, I think, is still somewhat controversial, but it's lost its importance because we wrote that paper in the hope that by introducing some new restrictions, you might be led to some new constructive progress, and that didn't happen, so it lost its importance. Well, now then I went to Cambridge. Actually, while I was in Rome, the situation changed drastically in Germany. I had been offered a job in Hamburg, an attractive position because it had been held previously or some years before by Pauli, so it was an attractive job. And I had decided to go. That would have meant foregoing the second half of my Rockefeller Fellowship because they were anxious to have somebody soon. And I'd agreed to that informally. But then things got so bad in Germany that we decided this was not right. We wouldn't go back.
These political developments about 1932.
That's right. It was the end of 32.
Yes, it made it intolerable.
Right, and it was before Hitler came to power, but you could see the way things were going, that we said, no, we're not returning to Germany. So we went to Cambridge as planned, where I had some contact with Dirac.
Oh, yes.
And also with R.H. Fowler, who was then the senior theoretical physicist in Cambridge. I saw quite a bit of Rutherford.
Oh, yes.
Very attractive, very impressive personality. But of course, this was for 6 months, and after that we had no job or anything. And however, the Lawrence Bragg, who was then in Manchester, he first hoped that he could appoint me to an assistant lecturership in the University of Manchester, but it turned out that the university was being attacked for appointing foreign scientists when they were British scientists without a job. There was a particular row made over the appointment of Polanyi, a chemist.
Such a very famous and distinguished chemist.
Right, but he was appointed to the chair of physical chemistry in Manchester, but some older chemists attacked this and wrote letters to newspapers and so on, so they felt they couldn't go on doing that. And instead I was giving a grant from a fund set up to help German refugees. Well, I wasn't technically a refugee because I was already out of Germany, but anyway, I got this grant. And we stayed for 2 years in Manchester. For the first of these 2 years, Beta was there too, so we worked together.
Oh yes, so you had Beta and you worked together right there at
Manchester.
Manchester.
This was first of all on solid state problems, because Bragg then was very interested in alloys and in the ordering in alloys, where you form superlattices, where of the two components of the lattice, the atoms are regularly arranged like A, B, or something, and that then is a thermodynamic problem because that happens only at low temperatures. And Bragg had himself with Williams, who was a first-rate physicist, worked out a crude theory of this phenomenon, and Bethe and I were not satisfied with that and felt one could improve it, and that resulted in a method now known as the Bethe method for getting answers to this type of problem. And also, however, this was when nuclear physics took off.
Oh yes, that was.
And, I think our interest in that started when Chadwick, who had discovered the neutron, told us, Bethe and myself, well, I don't remember his exact words, but essentially he said, I bet you can't make a theory of the disintegration of the neutron by gamma rays.
Oh, yes.
He didn't tell us that he already had done experiments on this.
Yeah, see, he was at the Cavendish laboratory at that time.
That's right. And so we felt that we could make a theory. And sat down and did some calculations on this. And that then involved also results about the scattering of neutrons by protons.
Oh, yes.
And we published 2 papers on these things. We had, they were beginning, but there were some facts which weren't known to us at the time, and so they were not a complete answer, but still we were pleased with what we did. And
well, this was almost immediately after the discovery of the neutron, wasn't it?
Yes, it was in, again, I'm not sure about the date, but Bethe was in Manchester from 33 to 34. Oh, yeah. So it was within a year of the discovery of the neutron, a year or so. And also, Fermi's theory of beta decay came out, and we got interested in that and published 2 small letters in Nature. Amongst other things, pointed out that the possibility of what's now called K-cap, that instead of the emission of a positive electron, the nucleus absorbs one of the atomic electrons surrounding it. And also, we pointed out in this paper that from statistical thermodynamic considerations, you could determine what was the cross-section for the inverse reaction where a neutrino gets captured by a nucleus, and that came out fantastically small, so small that, for example, a neutrino could go right through the Earth and come out at the other side with a negligible chance of having made a collision on the way. And so we said, probably the neutrinos would never be found, be picked up in experiments. And of course, in saying that, which by now, of course, has obviously been disproved, there were 2 things missing. One, we couldn't have known, of course, that about the enormous numbers of neutrinos that would be generated in nuclear reactors.
Oh, yes.
And that which led, in fact, to the work of Reines and others of actually catching these neutrinos. But the other factor we might have seen was that the cross-section for the capture of neutrinos goes up very fast with the energy.
Oh, yes.
And that while for the low energy of neutrinos which come out of beta decay, the cross-section is as small as we had estimated then. Once you get to a few billion electron volts, the cross-sections become become much greater, so much so that now everybody is doing experiments with neutrinos and being accelerated.
But your original theory on the probabilities, then it was you need a probe the size of the Earth to catch it.
Right. But that was at the energies which one was then
very low energy.
I did a variety of things then in Manchester, and then 2 years later, in 1935, I was offered a position in Cambridge at the Mond laboratory, which was a low-temperature laboratory set up for Kapitsa.
Mm-hmm.
Now, Kapitsa, who of course was a Russian working in Cambridge, had maintained his Soviet citizenship, and regularly, summer went back for his holidays to the Soviet Union, and as now known, in the summer of 1934, they refused him permission to leave again because they said they needed him in Soviet Union. And so eventually the Royal Society, who owned that laboratory, and the Cavendish laboratory agreed to all kinds of equipment to Moscow. The Soviet Union, of course, bought it from them, and with that money they duplicated the equipment to maintain the laboratory.
Oh, yes. What was the name of that laboratory now?
Mond, the Royal Society Mond Laboratory.
Mm-hmm.
Set up by, at least largely paid for by a donation from the Mond nickel.
Yes, they were famous. The company was famous for their nickel powder production.
That's one of the things.
One of the things.
Now that, however, left some money available which would have gone to Kapitsa's salary. And so they decided to use that money to set up 2 research fellowships, of which I got 1. And that brought me to Cambridge.
So you have the Soviet government to thank for your opportunity to go to Cambridge.
Then, I split my interest there in